here I am solving another Reddit physics problem. I don't know why. I'm like, hey, I got time, and I got other things I could be doing. But I thought I'd solve some problems. So here's one. I think it's a valid problem. Okay, so I had to find the electric field and the electric potential at point B. It's right down here. Which resulted in 36 coulombs. No. And that should be newtons per coulomb. And 1138 volts respectively. So let's do that problem. Okay. And then after that, we're going to add a charge ring over here with a radius of 2 centimeters and a charge of 1 nanocoulomb. Okay, that's not trivial, but I mean, it's not bad. I mean, I assume you're going to use the expression for the electric field due to a point charge, a ring, and the electric potential due to a ring, but I don't know. Okay, so let's just jump over to the paper and do this one. This one might take a little bit more time. That's fine. We got time. Okay, so let's draw the picture. It always helps to start with my own version of the picture. So here I have Q1, and then here I have Q2, and they're both 2 microcoulombs. So Q1 equals Q2 equals 2 microcoulombs. That's actually nice because it makes things work out a little bit easier. This is 10 centimeters, so 0.1 meter, 0.1 meter, and then here's point B right there, and this is 0.3 meters. So let's calculate the electric field, E. So the first thing to know is that the electric field due to a point charge is this. I can write E is KQ over R squared, R hat. Now, you may not like that, but that's the way it is. You may see this. E equals KQ over R squared. That's the scalar version, and in fact, we can get by with this. This way it's better in most cases. In this case, I think we can use this one, and that's probably what most people do. Very few people use this unit vector R hat, but it's way more powerful for more complicated situations. I'm going to actually do it this way, and just so you can see how it works. Now, if I have multiple charges, I just need to find the electric field due to each charge and add them up there. So if I look at this, here's charge 1. It's going to make an electric field like that, E1. And here's charge 2. It's going to make an electric field like that, E2. Now, what's really great about this and what it allows me to use this expression is that these have equal magnitudes, and they're symmetrical about this x-axis. I assume this is the x-axis. So if I add the vertical components of these electric fields, they're going to cancel, and I'm only going to be left with an electric field in the x direction. So that's pretty easy. I only have to deal with the x direction. So let's look at this angle theta, and in fact, they have the same x component. So if I find the x component of this electric field and multiply by 2, I'll be done. Okay, so let's see E1. Let's just find the magnitude. E1 is going to be this charge. It's going to be K. K is 9 times 10 to the 9th Newton meters squared per coulomb squared. That's like the Coulomb constant. It's also equal to 1 over 4 pi epsilon naught. Some people write it as K, some people write it as that. I'm just going to write it as K. So it's K times, let's call this R1. That's that distance. So it's K times Q1 over R1 squared. Now, what's R1? Well, let's just say, and I'll just use as numbers because I think that'll be easier here. R1, the magnitude, is going to be equal to, this is a right triangle, so I know this side's 0.3, that's 0.1, so R1 is going to be the square root of 0.3 squared plus 0.1 squared. So I know the value of that. Now, I also need to know this angle theta. But theta, if you look right here, I have a right triangle. So I can say tangent of theta is equal to the opposite over hypotenuse of the opposite over adjacent. So it's 0.1 over 0.3. But you could find theta if you wanted to, but I'm not gonna. Instead, I'm gonna say, well, I really want once I find the magnitude of this, I want to find this adjacent side is going to be that magnitude times cosine theta. So cosine theta is going to be the same angle as this, right? Because it's the same as that, which is adjacent over hypotenuse, which is 0.3 over R1. And I know R1. Okay. So let's put this in all together. E1x is going to be the electric field, K, times Q1 over R1 squared, which that's R1, times the cosine of theta, which is 0.3 over R1. And then I get that's going to be also equal to E2x, the same situation. So EX is going to be 2K times Q1 over R1 cubed, because I have R1 squared times R1 times 0.3. So let's go ahead and put in our values. 9 times 10 to the 9th, 0.3. And then this is going to be, I'll write this as 0.3 squared plus, no, let's just say R1 cubed. And so let's find R1 first. It'd just be easier. You could do it all in one fell swoop, and I would if I was using Python. But so I'm going to say square root of 0.3 squared plus 0.1 squared, close parentheses, and I get 0.316. And that's in meters, technically. So then down here, I can put everything in. Oh, I didn't put my charge, Q. Q is 2 microcoulombs. So I have 2 times 10 to the negative 6. Okay, so let's put all that in. So I'm going to say 2 times 9 times 10 to the 9th times 0.3 times 2 times 10 to the negative 6 divided by 0.316 to the, I'm not good with calculators, to tell you the truth. I'm looking for the raised power. I don't see it because I'm a dummy. There it is. Let's see if that works. And I get 33.4 times 10 to the 5th newtons per coulomb. And that's not what they got in the book. Micro. And the page said they got 36. Well, I like my answer better. Okay. Now, what about the electric potential? So the potential, we do the same thing. The only difference is that the potential due to a point charge is a scalar value. So V equals KQ over R. So I can again calculate this as Q1 over R1 plus KQ2 over R2. But I already know R1, and these is the same as R2. So this is really just going to be 2KQ1 over R1. That's it. So let's just put that in. 2 times 9 times 10 to the 9th times 2 times 10 to the negative 6, all over 0.316, which I already calculated. So if I put that in, I get clear 2 times 9 times 10 to the 9th times 2 times, you got to hit it really hard. It makes you feel better. Negative 6 divided by 0.316, enter. I get 1.139 times 10 to the 5th volts, which they had just 1,000. So that would be 10 to the 3rd, but okay, I'd like my answer. They may have used, oh, I see. It says in the problem microcoulombs, but they have different values. It says the picture, but they say R is 2 centimeters. Oh, no, I guess not. That's weird. Okay. So, but now what happens if I add this ring in? So here I have my positive charge, Q1, Q2, and then here's point B, and then I have this ring of charge. So this ring has a charge of I'll call it Q3 is 1 nanocoulomb, and our ring, RR, is 0.02 meters. And then this is 5 centimeters. So this distance is 0.05 meters. Now, the electric field due to a ring is derivable, and it's not even hard. But I don't want to actually derive that at this point. So I'm just going to look up the equation, which I already had because I saw this problem. And I actually have a video on how to derive the electric field due to a ring. And it turns out that if this is positively charged, this will make an electric field in the x-axis going that way. So I'll have E ring, and then I have E1 and E2. But I already found the sum of E1 and E2 as a vector going that way. So if I take that electric field, subtract the electric field from this, I'll get the net electric field in the x direction. So let's do that. So I know due to a ring, EX is going to be equal to K times X Q over, I'm going to use capital R squared plus X squared to the 3/2. So in this equation, if I have my ring right here, this is X, the distance from there, and that's R. So in my case, X is going to be 0.05, which I know is kind of really weird. So let's just find the electric field due to the ring. I'll call it ER in the X direction. It's going to be 9 times 10 to the 9th, 0.05. Q is 1 times 10 to the negative 9th. No, yes. All that over 0.02 squared plus 0.05 squared to the 3/2. Okay, that's a lot. Let's just do it though. Let's see if we can get this in the calculator. So I have 9 times 10 to the 9th times 0.05 times 1 times 10 to the negative 9th divided by parentheses 0.02 squared plus 0.05 squared, close parentheses, hat, parentheses, 3 divided by 2, close parentheses, please work. And I get 2.88 times 10 to the 3rd. But that's in the negative x direction. So now my total electric field, E, is going to be E12 minus ER. So if I use my value from before, which is 3.4 times 10 to the 5th, so it's going to be 3.4 times 10 to the 5th minus 2.88 times 10 to the 3rd, I get, can I just do minus? No. I'm not very good with calculators. So I get 3.4 times 10 to the 5th minus 2.88 times 10 to the 3rd equals, I get 3.37 times 10 to the 5th newtons per coulomb. And that's the magnitude electric field. It's in the x direction though. It's in the positive x direction. So you'll notice that these two charges, the sum of these two charges, makes an electric field that's greater in the x direction than this ring, even though the ring's closer, because the ring has a charge, a very, very small charge of 1 nanocoulomb. And these are microcoulombs. So, okay. That's it.